As I mentioned for today's lecture, I want to focus on this last topic here. This is how do you accelerate consolidation settlement. To introduce these different types of methods, I want to use this example here. So this is actual example 4. For this example, you're given this large development of basically residential buildings along Bay Area. So the data we use corresponds to Bay mud or this soft clay. And the site is to be preloaded by 10 feet of sandy fill on top. Again, we're preloading the site. And the target is to reach 90% degree consolidation before we start our construction. In this, the soil profile is given. So we have soft clay, bay mud, and the depth or the thickness of this clay layer is 50 feet. Okay. We have sandy fill on top. Again, that's permeable. And this bedrock at the bottom, we treat it as impermeable layer. So let's first calculate how long it will take to reach 90 degree consolidation. And so part 1. We just did this calculation in the previous example. So basically we have this TV. Okay. So for U of 90%, okay. Again, table 11.7, we have done this a number of times. So the time factor corresponding to 90% degree consolidation, 0.848. 848, okay. And then we can calculate small t. And for that, we need HDR. So HDR, this is one-way drainage. And HDR is 50 feet. Okay, thickness of the consolidating layer for one-way drainage. Okay. So then we can calculate time t. And C sub V, 25 feet squared per year, that's given. You can get this from 1D consolidation test. Okay. So if you're substituting all these numbers, HDR 50, and C sub V 25. Okay. Just plugging all these numbers in, you will get small t of 85 years. So that's the time it will take if you don't do anything else. Just for this 1D consolidation, it will take 85 years for that site to reach 90% degree of consolidation. So clearly that's not practical at all. So nobody can wait for 85 years for the clay to consolidate. So let's look at the issue here. So what causes the problem? So why it takes so long for clay to consolidate here? So if you look at this time factor, so TV, so this is CV small t in HDR squared. And from this definition, that's how we calculate that small t of 85 years. So in this expression here, this small time t, so I want to highlight two things here. Use a different color here. So one is this HDR. And the other one is C sub V here. So if you look at these two parameters here, so this T. So this T is proportional to HDR squared. And T is also proportional to basically inverse of this C sub V. In C sub V, we just showed, let me actually go back. So if you look at here, so C sub V, this is related to the permeability of clay. And we know for clay, K is very small, so that permeability is very small. So therefore, if you plug in this into C sub V, you notice that this, because K is very small, so this inverse ratio is large, so your T is large. And also, if your drainage distance HDR is large, then you get a large T as well. So therefore, if we identify the issues, then the way to actually accelerate consolidation is to, okay, so solution. So one way to accelerate this consolidation process, basically to reduce T, is to reduce HDR. One option is we can reduce the drainage distance, HDR. If you reduce HDR, and T will reduce by HDR to the power 2, basically HDR squared. And the second is to increase C sub V. If you somehow increase the coefficient of consolidation, T, that small t will decrease. So that's the solution. So that's the idea behind this next set of methods I'm going to introduce. And so there are different types of methods. The first one, this is called sand drains. Okay. So all these methods, sand drain and also the PVDs I'm going to introduce, so they're trying to, one, reduce that drainage distance, and two, increase coefficient of consolidation. Okay. So first for sand drains here, if you look at this sketch here, so we have these pre-drilled holes. So this is our holes. So these are pre-drilled holes at regular intervals through your clay layer. Okay. So you have this, so this is your clay layer. That's your consolidating layer. In these pre-drilled holes, you backfill them with sand. Okay, so you fill them with sand. Okay. So these sand drains, they do two things. First, they actually provide a radial drainage path. So remember previously for that 1D consolidation, the only way out for clay is through either at the top or at the bottom, depending on the layer there. So it's only just a one-way drainage in the vertical direction. But if you add sand drains, there's additional way for water to escape. Okay. So that's a radial drainage path. Okay. So effectively, you're dramatically decreasing the drainage distance. Okay. So HDR gets reduced. And second, because water flows horizontally, and this basically relates to what we discussed in chapter 7, permeability. So permeability, if you recall, for natural soil, it's actually easier for water to flow horizontally because the permeability along horizontal direction is much larger. Okay. So actually, the second effect of this radial drainage is you're increasing the permeability and therefore increasing coefficient of consolidation. Okay. So that's the idea behind these methods here. So sand drain, and so on the right-hand side, this is a pattern for typical sand drain. And I'm going to actually use a different notation here. Actually, we're going to use this notation in the example later. So I'm going to call this small d w. Okay. So that's the radius of the sand drain, basically that hole you drilled into the ground. And this picture shows basically the installation of sand drains. As I mentioned, you need to basically drill holes in the ground and then backfill that with sands. And then you put your surcharge on top. So you put your sandy fill on top. And this one here basically shows as you put surcharge on top, water drains out. It basically shoots out through these sandy drains here. One potential issue with sand drains method is with installation. Okay. So ideally, so you're basically drilling these cylindrical shaped holes in the ground and backfill them with sand. But in actual installation, you may encounter with different soil profiles, and the actual sand drain tubes may look something like this. Okay. So that leads to the second type of method. This is called prefabricated vertical drains, or PVDs. So this method, PVD, is also called weak or strip drains. In this method, you don't need to pre-drill holes. So you have basically this polypropylene core and wrapped with some geotextile fabric, basically to provide that drainage path. And instead of go through that sandy drains, water will basically penetrate this fabric and get drained through these PVDs. So compared to the sandy drain, so advantage of this PVD is it's actually a much faster installation. And because you don't have to pre-drill and backfill sand, it's actually easier to control the quality of these PVDs, these vertical drains. So this sets of pictures basically shows example of PVDs installation. And these are, if you look at this picture here, so these are basically all PVDs. And this is a zoom in view. And again, you see water drains from the PVDs. Okay. After you put surcharge, water is going to drain through these PVDs. And finally, back to that example I showed at the beginning. So I want to show a quick calculation. Say if we have a horizontal drainage provided, say PVD or sand drains, how do we calculate the new time to reach 90-degree consolidation? So this is where we have this horizontal drainage, radial drainage. And this can come from either sand drains or the PVDs. And this time rate of consolidation, again, very similar expression. The difference here is this C sub VH. So this C sub VH is coefficient of consolidation, but in the horizontal direction. So it's horizontal direction. And then on the right-hand side, this is, if you think of Terzaghi solution, so this is that solution for horizontal drainage case. So we have time factor, T sub V, and T sub H here. So this is for horizontal drainage. So it's that time factor used in this small t calculation for horizontal drainage. And in the vertical axis, this is basically still U. Okay, that's the average degree consolidation here. Okay. But you have UB and UH. So then for these lines here, if you look at this solution, this small n value, okay, so that's for the solid lines. Solid lines are for radial drainage. Okay. So these small n values depend on the diameter of the drain and also the spacing of the drains. And I'll explain these two parameters, capital D and dW. So in this plan here, if you look at this, there are basically two plans for vertical drains. One is called a square pattern. So you have those are vertical drains. So one is square pattern, the other one is triangular pattern. And small dW in the previous equation is the diameter of the vertical drain. And then that capital D, so it's the diameter of this tributary drained area. So D is actually diameter. So D is the diameter of the tributary area. So let me go back here. Okay. And this D, capital D, is for square pattern, is 1.13 times S, which is the spacing between the vertical drains. Okay. So S. And for triangular pattern, this capital D is 1.05 times S. Okay. So that's for two common types of patterns for horizontal drains. So with all this information, then we can finish that extra example. So let's recalculate that time t if you have radial drains. So for this extra example, so we're going to actually install vertical drains to provide that radial drainage of 0.5 this diameter. So this is a small dw. In the spacing of 5 feet, S is 5 feet. In triangular pattern, because we have this triangular pattern. And now let's calculate that small t. Okay. So we have S and from the previous slide, I showed you that for triangular pattern, its capital D is 1.05 times capital S. And if you plug in S of 5 feet, this is 5.25 feet. So that's capital D. And then dW, the diameter of the vertical drain is 0.5 feet. And then we can calculate that small n we need to get time factor. So this small n. So it's 5.25 over 0.5. So D over small d, capital D over small d. And this is 10.5. So that's small n. And from this solution here, this figure, our target is 90% degree of consolidation. So that's our target. In vertical drain case, we use table 11.7 to find the corresponding time factor. And for this horizontal or radial drainage case, we're going to use this figure here. So this 90%, if you go to the solution, remember our n value is 10.5, so it's about 10. Okay. So this small n is approximately 10. So 10 is this solid curve here. Okay. So you can actually find the corresponding time factor for radial drainage case from this solution chart. Okay. And this is T sub V approximately TH, excuse me. So T sub H approximately 0.45. So that's how you get your time factor. Again, if it's just a vertical drainage case, we just use table 11.7 to find time factor. But because we have this horizontal radial drain, we need to use this chart here. Okay. So that gives you T sub H. So that's time factor for radial drainage. Okay. Then .45. Okay. So this is from that figure in the previous slide. Once we have this T sub V, then small t is T sub H. In this case, okay, the other thing, for radial drainage, your HDR. Okay. So for radial drainage, because water flows horizontally, actually the drainage distance is that capital D. Okay, so that's the radius of that tributary area. Okay. So this is for radial drainage. And then this T sub V, so HDR. And in this expression, the only thing missing is the horizontal coefficient of consolidation. Okay, so C sub V. So the horizontal coefficient consolidation, just a rule of thumb, is typically 4 to 5 times the vertical one. So C sub V. Okay. So for this problem, we're given C sub V of 25. Okay. So let's use 4 times. And that's 100 feet square per year. Okay. So this is coefficient of consolidation in the vertical direction. It's basically our typical C sub V. Okay. That's 25 feet square per year. And if you substitute all these numbers, so that's 0.45. And HDR here is that capital D, 5.25 square over C sub V horizontal 100. If you plug in all these numbers and convert final results to month, this is so get a time T in this case of only 1.5 months. So that is much more manageable for a construction project. So this means after you put that surcharge on top, it's going to take about 1.5 months for that clay layer to reach 90% degree consolidation. So compare this with part A, which is about 85 years. Okay. So by providing this drainage, horizontal drainage paths, by installing these vertical drains, you actually substantially accelerate the consolidation process.